In this screencast, we're going to talk about how amino acids react to form polymers that lead us to proteins. And then we're going to talk about some of the different structures of proteins leading up to three-dimensional structures of proteins and some of those intermolecular forces that help with that. So we're going to start with a condensation reaction, and we looked at condensation reactions in chapter 5. And we also saw condensation reactions when we looked at the formation of ester bonds. And so if you remember, there's a functional group, the carboxylic acid group reacts with a functional group, the alcohol group, and that forms an ester. This is one of the ways that triglycerides and phospholipids are formed when we have fatty acids and glycerols that react. And one of the things you can see, or something that's kind of analogous to this, is that with peptide bond formation between the amino acids, one amino acid will have a carboxylate group and another amino acid will have an amine group, and these two react and they form an amide bond. And I just want to remind you, an amide bond is a C double bond O with the nitrogen group here. When we talk about this, look and notice that water is removed from both of these. So when we see here, notice in red, there's an OH here and an H here, and that forms water here. We've also seen condensation reactions in the formation of a glycoside acidic bond with carbohydrates. And that same kind of idea, we have a hemiacetal functional group reacting with an alcohol functional group, and we have a glycoside bond. So these are all examples of those condensation reactions. And then this is the one that we're really going to focus on, right? Because that's that peptide bond that's formed. So let's put some words to this then. When amino acids combine, okay, an amide bond forms. That is called the peptide bond. Okay. In the dipeptide, there's an N-terminus. Okay. And sometimes this is known as an amino terminus, but an N-terminus. And it has an unreacted alpha amino group. Okay. And that N-terminus is shown right here, and there's the unreacted alpha amino group there. Okay. Then in this peptide bond, we will also have a C-terminus. And in the C-terminus, it's also called a carboxy terminus. It has an unreacted carboxylate group. Right? And so you can see that unreacted carboxylate group here. Now, by convention, peptides are always written from the N-terminus to the C-terminus. Okay, so we start here with the N-terminus where that unreacted alpha amino group is, and then we read the peptide from left to right from the N-terminus to the C-terminus. And so this is how it's written. So when we see alanine and valine combine in a condensation reaction, we end up with a dipeptide. And we see the dipeptide written here, but you can also write it using the 3 letter designations here and then the one-letter designations here. So lots of examples of how you can see these written. Now, if you have a peptide and you need to identify the components, here are some steps that are outlined. So the first thing that you would want to do is you would want to circle the amino acid at the N-terminus. And so we find the N-terminus and we're going to circle the amino acid there, okay? Then what you're going to do is you're going to put a square around the amino acid at the C-terminus. So I'm going to come here and I'm going to choose, let's choose purple. That's a really fun color, right? And then here is the amino acid at the C-terminus, okay? And then you can locate the peptide bond by drawing an arrow to it. And they already have a peptide bond arrow, but I'm also going to draw an arrow right there. So then once you identify the individual peptides, you can give their 3-letter and 1-letter abbreviations for the dipeptide or a longer peptide. Now, I just want to make sure that you're going to hear me talk about proteins, but we're also going to talk about peptides. Peptides are shorter kind of connections of amino acids that are not quite to the level of proteins. So proteins generally have, and this is a moving definition, but 30 to 40 to 50 amino acids. And so a peptide is just a smaller linkage of those amino acids. So let's talk about dipeptides for a second. We've seen this di prefix before when we talked about carbohydrates like disaccharides. And so we know that this prefix means 2. And so when we talk about dipeptides, these are formed between any 2 amino acids, okay? And then each pair can combine to form different dipeptides. Now, these dipeptides would have different properties. So look at the example here. This is written, again, these are written from the N-terminus to C-terminus. So if alanine comes first and then valine, that is not the same as saying valine and then alanine. So these are 2 different peptides. Right? And these are actually structural isomers of each other. Right? Now, the order of amino acids is critical to the structure. And the function of the compound or the peptide, right? So the order is very important. So we want to make sure that we don't confuse the orders here. Now, I mentioned this before, but I just want to put some words to what was mentioned, right? Any compound containing amino acids joined by a peptide bond can be called a dipeptide, right? Now, dipeptides are the smallest peptide. We don't have monopeptides because those are just amino acids. So dipeptides are the smallest. If you have 3 amino acids, and I'm going to abbreviate amino acids with AA, that would be a tripeptide, where the tri prefix indicates 3. If you had 4 amino acids, that would be a tetrapeptide. Okay, and so on and so on. And we're using the same prefixes here that we did when we named covalent compounds. So the same prefixes repeat there. As the number of amino acids increases, we kind of drop those prefixes and just generically call the compound a polypeptide. So those prefixes are dropped, and the compound is referred to as a polypeptide. Now, a biologically active polypeptide that contains 50 or more amino acids is a protein. This is how your book defines it, but it's a little bit more of a moving target. I've seen books define it as few as 30 and then 40, but we are going to go with what your book says. So a protein is just a biologically active polypeptide containing 50 or more amino acids. Okay, and that's referred to as a protein. Now, let's talk about proteins and amino acids and some applications of this. So a substance called gluten, right, is a mixture of proteins that are found in various grains. Right, including wheat, right? So they're found in various grains. The two main proteins are glutenin and gliadin, right? And these both contain regions that are rich in the amino acids proline and glutamine. Okay, now that's a pretty unique amino acid sequence. Okay, so when gluten enters the digestive system, some of the peptide bonds are hydrolyzed by enzymes called proteases. And these break down the gluten and leave behind proline and glutamine rich peptides in the digestive system. Now, some of the glutamines in these fragments are modified by to glutamate by an enzyme called glutaminase. Okay, so a few things here. If something ends in an ASE, that's an indication that it's an enzyme. So what happens is this protein is hydrolyzed. We end up with glutamine here, right? Glutaminase reacts with it. And during this reaction, water, so glutamine reacts with water in the enzyme glutamase, and ammonia is a product. And this is formed into glutamate. Glutamate is the product here as well. So one of the things to be aware of is that transition takes this from a polar neutral residue, so this guy is polar neutral, to a polar acidic residue, okay? And the addition of the negative charge to the peptide sequence causes people with celiac disease to launch an immune response against those peptides. Okay, and so symptoms here include inflammation of the small intestine, low intestinal absorption of nutrients, and then malnutrition. And the treatment for it is just to avoid gluten, right? And so celiac disease is an example of where the polar charges on amino acids can really affect certain people's health, right? Now, let's talk about the three-dimensional structure of proteins. We've already talked somewhat about a primary structure of proteins, and the primary structure of proteins is just the amino acid sequence. Right? And that's just the order in which the amino acids are joined together. Now, they're going to form a protein backbone. And so when we talk about a protein backbone, that's shown right there. And that lines up from the N terminus to the C terminus. Okay? So one of the things that you can notice is the substituents are shown here in blue, and they are dangling off the backbone. So we have the protein backbone here, and then the side chains or the substituents are kind of poking out from that backbone. And this is the primary structure. Now, the secondary structure of a protein is going to involve regions that can form coils or repeating patterns of structure and really form a three-dimensional shape. So when we talk about secondary structure, we have secondary structure that's written like this. You will also sometimes see it as secondary with a like a degree sign. I cannot go back, but I meant to write this on the previous slide. Primary structure can also be shown like that. All right, so we have secondary structure here, and the two most common secondary structures are an alpha helix or an alpha helices. And a synonym for this is just the alpha like this and the helix. And then the second one is a beta pleated sheet. And instead of doing beta, you can use that notation. The secondary structures in proteins are stabilized by hydrogen bonding along the protein backbone, right? And they involve these amino acids that are near each other and the intermolecular forces between them. Now, remember, hydrogen bonding is not a covalent bond, but just a strong attractive force. And if you need to go back and review that, we talked about that in chapter 7. So let's dig a little bit more into alpha helices and beta pleated sheet. So when we talk about an alpha helix, this is a coiled structure. And there's an image here on the slide. Stabilized by hydrogen bonds formed between the carbonyl oxygen atom of one amino acid and the nitrogen and hydrogen atom of another amino acid. And it's not, when we talk about this, it's not just another amino acid, but there's a really kind of specific pattern. It's the fourth amino acid away from the primary structure. And so this is what lends us to the coil, is this regular spacing. So that position of the hydrogen bond allows the helix to stretch and recoil. Okay, and multiple hydrogen bond interactions make that helix a really strong structure. In the alpha helices, the side chains of amino acids project outward away from the axis of the helix. And so we can see those right in here. Okay. Now, with beta pleated sheets, this is an extended structure. Where segments of the protein chain align to form a zigzag structure. And this is analogous to a paper folding, right? So you can see kind of like if you were to accordion a paper, okay? That's one of the ways it folds there. These are held together side by side by hydrogen bond interactions between their backbones. Right? And then in the beta pleated sheet, the side chains of the amino acids project above and below the sheet. And so that's where we see that. Now the hydrogen bonds are shown right here. So you can see the hydrogen bonds between the peptide backbones. Now, secondary structure comes into play with diseases like Alzheimer's disease. Alzheimer's disease is a common form of dementia that causes memory loss and the inability to think clearly, and that becomes severe enough to interfere with daily tasks. The disease is progressive and most often occurs in adults over the age of 65. And while there's not a cure, what we do know is that people with this disease have distinctly different brain tissue than people without the disease. So the brain tissue of people with Alzheimer's disease contains plaques between the brain's nerve cells. Okay, so if this was a normal brain here, you would see the plaques that were between the cells here. Okay, and those buildup of plaques and what are called neurofibrilla tangles inside the neurons are thought to interfere with the nerve impulse transmissions and contribute to neuron death. Okay, the protein plaques are made up of a protein fragment of about 42 amino acids long. So the plaques are protein fragments of approximately 42 amino acids long, and they are called beta amyloid proteins. And the protein sequence has been identified in both healthy and diseased individuals. In a person without Alzheimer's, the structure of the beta amyloid plaques is alpha helical. So this would be what it normally would look like. But in a person with Alzheimer's, right, those beta amyloid proteins form beta strands instead. And that change makes the beta amyloid proteins fold into a sticky beta pleated sheet. And those sheets aggregate to form the plaques at the neurons. Now, as I mentioned before, there's no cure for Alzheimer's disease, but medications have been developed that can slow its progression or lessen the symptoms for a limited time by keeping the levels of brain's transmitters high. I've had two grandparents who have passed away from Alzheimer's disease, about 10 years apart. And I said, and one of them, these medicines were not available, and she could not recognize us pretty quickly. And then my other grandmother, these medications were available, and she lived with Alzheimer's for a really long time and could still remember and recognize us, and even remembered when I changed my hair and did things like that. So there's been a lot of research in that area. Now, let's talk about tertiary structure. When we talk about tertiary structure, the alpha helices and the beta pleated sheets interact with each other in the environment, and they create a three-dimensional structure that's called a tertiary structure. One of the other things that happens with this tertiary structure is we get some what are called hydrophobic effects, where nonpolar side chains are repelled by an aqueous environment and turn toward the interior of the protein. Okay. Now, polar side chains are attracted to aqueous surroundings and appear on the surface. Right? And then the tertiary structure is stabilized by attractive forces between side chains and the environment. So when we look at all of the different interactions, we have things like that are called salt bridges, but you can recognize these as ionic bonds as well. We have hydrogen bonds here, disulfide bonds. We see more hydrogen bonds here, hydrogen bonds. Hydrophobic interactions, which we also know are things like van der Waals interactions or London dispersion forces. And then the hydrogen bond here to water. So remember, we're large aqueous things, and so we're going to have water that surrounds this whole protein. And so all of these interactions cause proteins to fold in the way that they do. So let's talk about these interactions individually. So here are kind of four big ones. So we have nonpolar interactions, where we have nonpolar amino acid side chains are repelled by the aqueous environment and aggregate in the interior of the protein. Then we have polar interactions, and in polar interactions, polar amino acid side chains interact with water and each other through dipole interactions, ion dipole interactions, and hydrogen bonding interactions. Then we have salt bridges, which are also known as ionic interactions, and these are interactions between a positive and a negative charge. And then we have disulfide bonds and we can see the disulfide bonds here, where we have two thiols that react to form that disulfide bond. Now, this is a covalent bond. Okay. Now, with all of this folding, we end up with two kind of large classifications of proteins. Those two large classifications of proteins are globular proteins or fibrous proteins. Now, globular proteins will fold into compact, spherical shapes with polar amino acid side chains on the surface and nonpolar side chains in the core, right? And so we see this, many enzymes are these globular proteins, kind of imagine like a sphere, right? They're spherical. And a lot of the cellular proteins are also globular. Then we can also have fibrous proteins, and these have a long thread-like structure. Okay, and we have aligned helices here, and they form these really long, durable structures, and these tend to be insoluble in water, while most of your globular proteins tend to be soluble. So, for example, right, hair is a really good example of a fibrous protein. Now, we also have quaternary structure, and sometimes quaternary structure is shown with a 4 in degree. A tertiary structure will be shown with a 3 in a degree sign. And this describes the interactions of two or more polypeptide chains that form a single biologically active protein. Right? And the individual polypeptide chains or subunits are held together by the same interactions that stabilize the tertiary structure of a single protein. Not all biologically active proteins have a quaternary structure. Some are just made up of a single polypeptide chain, but some of them do. And so that's why we mention it and talk about it. So I know that's a lot to take in, and this is a really helpful review table and an image, because everybody's kind of a different learner. So you may love tables or you may love images, but the primary structure is just the amino acid sequence. It's those peptide bonds. Here's the primary structure. And then the secondary structure is caused from hydrogen bonding along the protein backbone, and it's between the amino acids that are close to each other. And remember, we talked about alpha helices and beta pleated sheets. And so this is one of the examples. That's an alpha helices. That's a secondary structure. Then we have tertiary that folds, and that folding is due to London dispersion forces or hydrogen bonding or dipole-dipole or ion-dipole, ionic salt bridges and disulfide bonds. So lots and lots of intermolecular forces and covalent bonding there between the R groups of the amino acids that are far away from each other. And then remember, we have those hydrophobic interactions too, where there's water kind of around here, right? And it kind of forces these to form. And then we end up the same when we talk about tertiary structure here, or quaternary structure. Tertiary structure is, Quaternary structure is the same basically as tertiary structure, but it's when we get a lot of different subunits that come together. So if this is one large polypeptide, you can end up with 4 polypeptides that come together to give a quaternary structure. So if you have any questions, please feel free to reach out. In the next screencast, we are going to talk about some of the functions of peptides and proteins.